Hi everyone, welcome back to another GCSE Physics webinar. Today is going to be on alpha, beta and gamma radiation. So if you were here yesterday, it's just a follow-on from there. Today's session is going to be 1 hour long, and as always, it will be recorded and uploaded onto YouTube later so that you can refresh and revise the content or get down any notes that you didn't manage to get down. So if you don't know me already, my name is Preshayla and I study physics at Loughborough University. It's my 4th year as a tutor and I'm the GCSE Physics tutor for the online school. What we'll cover today is the below. So how can we compare alpha, beta and gamma radiation? So what kind of factors can we compare between the three of them? Understand what penetrating power and ionizing power is. Understand what radiation is and what kind of radiation is appropriate for different uses. Know what the activity of a source is defined as and what kind of units we use to measure it in. And then finally, to know what the half-life of a source is and how to calculate it. We'll go through example questions and I'll take your questions at the end as well. If you guys do have any questions throughout the session, then please put them on the chat function or the Q&A function so I can see them and I'll try to get to them as quickly as possible. Okay, so as I said, today's content is going to be all about alpha, beta and gamma radiation. But first, let's go through a summary of what we covered yesterday. So first of all, we looked at what stops alpha and beta radiation. So if we have a source which is emitting alpha or beta, how can we block that radiation? Well, we talked about alpha and we said that even if we were to put a really thin sheet of paper in between the source and the detector, alpha would be blocked. Okay, so no alpha particles can get through even the smallest thickness of paper. Okay, so alpha can be stopped really easily, and we're going to look a lot more in depth about this today. Then we talked about what experiment led to the discovery of the nucleus. So this was talking about the gold foil experiment and how Rutherford shot alpha particles at a piece of gold foil. He then realized that most of the alpha particles went through, some kind of bended in their path, and some rebounded all the way back. So because of this rebound, Rutherford said that there is some kind of repulsion. And because there's repulsion, there must be two like charges. Now, he already knew that alpha was positively charged. So he said that there must be some positive charge in atoms, which makes this repulsion happen. And this therefore led to the fact that he thought that there was a positive charge in the atom in the nucleus. This led to the plum pudding model. The plum pudding model is a kind of sphere of positive charge with electrons dotted around it. Now the electrons are supposed to be the plums and the kind of sea of positive charge, the sphere of positive charge, is the pudding. So the first model of the atom is this idea of the plum pudding. However, Bohr then went on, who's a new scientist, to disprove this theory. And he said, actually, this is not true. He said, there is a positive charge, there is a sphere of positive charge, but it's in the center. And instead of having little plums of electrons, we now have the electrons in orbits around the nucleus. So he said that there are these orbits of electrons called shells, and each shell has its own energy and can fit a certain amount of electrons on. He also said that electrons can jump between shells. They can go to the outer shell or the inner shell, depending on whether they absorb or emit electromagnetic radiation. So then there were more alpha scattering experiments done, and they deduced more and more things about the model of the atom. The final thing that was found is the existence of the neutron. There was some missing mass, and this was theorized to be in the form of a neutron. So they came up finally with this final kind of form of the atom, which is what is accepted today. And that is that the nucleus, the inside sphere, where most of the mass is, has protons and neutrons. So they're in the inside sphere. And then Bohr's predictions are still true today, that the electrons orbit in shells around the nucleus. So we now finally have our final model of the atom. Then we went on to look a little bit at alpha, beta, and gamma decay. So in beta decay, we found that beta is actually just an electron. This changes the atomic number by 1. The atomic number increases by 1. And the mass number does not change because it's only protons that we're dealing with. In alpha decay, however, the atomic number, the number of protons, changes by 2, decreases by 2, and the mass number changes by 4. Then we talked about what is the relative mass and charge of the proton, neutron, and electron. Well, we said that the mass of the proton is 1, the mass of the neutron is 1, but the mass of the electron is so small that we can just discount it. It's negligible because it's so small. Then we talked about the charges on each of those particles. So the charge on a proton was 1, charge on a neutron was 0, and the charge on an electron was -1. We talked about isotopes, which are 2 forms of the same element, which have the same number of protons, but a different number of neutrons. So therefore, their atomic numbers are the same, but their mass numbers are different. We talked about why some substances are radioactive, and this is because of how stable or unstable the nucleus is. Radioactive decay happens so that the nucleus can become more and more stable. Then we finally talked about what actually is alpha, beta, and gamma emission. So that was saying that alpha is a helium nucleus, beta is an electron or a stream of electrons, and gamma is a gamma electromagnetic wave. So let's go and refresh alpha, beta, and gamma radiation. So let's start with alpha. Now, alpha is the nucleus of the helium atom. It does not take the electrons, only the nucleus. Okay, so these blue and green dots here is the nucleus. Now, the alpha particle is that helium nucleus only. It doesn't take the electrons from helium with it, it's just the nucleus. That's really important. So when we're describing an alpha particle, we must say helium nucleus, not helium atom. Because if we say helium atom, that infers that we are including the electrons, which is not true. Beta, however, is formed of electrons, but not the electrons that we kind of think and see in atoms. So it's not these electrons which are in shells. It's actually a neutron turning to a proton and spitting out an electron. So beta decay comes from neutrons turning into protons and releasing electrons. Beta decay is not the electrons in the shell of an atom. It's a different type of an electron. Finally, then, we looked at gamma. So gamma is an electromagnetic wave with high frequency and short wavelength. So think right back to the electromagnetic spectrum. We have radio waves and microwaves all the way up to gamma rays. And gamma rays were our final kind of part of the spectrum, where we have the highest frequency and the shortest wavelength. So all gamma is an electromagnetic wave. That's what EM stands for. Okay, so we know in depth about what each of these radiations are. Now, how can we compare and contrast them? Well, there's 3 main things that scientists use and that you're expected to think about in your GCSE. These two things are penetrating power, ionizing power, and the range that they have in air. So let's first look at the penetrating power. Well, we know that alpha is pretty weak. It can be stopped by skin or paper. Beta is a lot more penetrating, and it can get through skin and paper, but it will be blocked by a certain thickness of foil. Gamma is very penetrating, and it can get through skin, it can get through paper, it can get through foil, but it will be stopped by lead or concrete. So you need to memorize this table, and you need to be able to talk about the penetrating power of all three and give examples of materials that they will be blocked by. So alpha, again, will be blocked by skin or paper. Beta will be blocked by certain thicknesses of foil. And gamma will be blocked by certain thicknesses of lead or concrete. Then we can compare their ionizing powers. Now we'll talk more about ionizing powers in a second, but what you need to know for now is that alpha has the highest ionizing power, beta has a lower ionizing power, and gamma has the lowest ionizing power. Okay, so the penetrating power and the ionizing power are opposites. Whilst alpha is the most penetrating, the least penetrating, alpha is the highest ionizing. Okay, so penetrating goes from lowest to highest, and ionizing goes from highest to lowest. So the third thing that we can compare them with is their range in air. Alpha can only last for 5 centimeters in air. It will only affect an object if it's less than 5 centimeters. Beta can range up to 1 meter, and gamma can go for a whole kilometer. So as I said, this table has to be memorized because you will be expected to pull out these facts in an exam question. Okay, so here's another diagram of penetrating power, and it just shows that alpha can be blocked by paper, beta can be blocked by some form of aluminium foil, and gamma can be blocked by lead. So let's talk more in depth about ionizing power and ionizing radiation. So ionizing radiation is bad in most cases. Ionizing radiation is what damages human cells. So radiation from a radioactive substance can knock electrons out of an atom. Okay, so we have our radioactive substance. It might be barium, beryllium, lithium, some sort of radioactive substance, which gives out some radiation. Now, this radiation can knock electrons out of an atom. So it hits an atom and it bombards these electron shells, knocks them out of place. Now, if an atom loses electrons, it will become charged. Okay, so if it loses electrons, it becomes charged. This process is called ionization. It's called ionization because an ion is a charged particle. So when we knock the electrons out of an atom, we become charged. Our atom becomes charged, and it therefore turns into an ion, which is a charged particle. Now, alpha is the most dangerous because it has the highest ionizing power. It's able to knock out lots of electrons and make it into charged atoms. So alpha is the most dangerous to humans as it has the highest ionizing power. But you'll remember that alpha can actually be really easily blocked. So to reduce our risk, we can keep as far away from it as possible by using special tools to handle sources that emit alpha, spending as little time as possible near it, so reducing our exposure time, and we can shield it using thick lead plates. So there's lots of things that we can do to reduce our risk of getting alpha radiation in or near our bodies. So it's dangerous because it has the highest ionizing power. We do not want charged particles in our bodies, basically. Okay, so although radiation can be dangerous, and most of the time it is very dangerous, there are some uses for it as well. But it's important that when we are using radiation, we use the appropriate type of radiation for what we need it for. So when we're picking between alpha, beta, and gamma, which one we're going to use, we have to think very carefully about the application we're putting it in. So one application that you need to know for your GCSE is the application of the smoke alarm. So smoke alarms have a radioactive substance in them. Again, could be beryllium, could be lithium, whatever, as long as it emits alpha in its majority. Okay, so we want an alpha emitting source in our smoke alarm. Now those alpha particles coming out of the substance ionize air. Okay, ionizes the atoms in air, in a gap in a circuit. So it gives out alpha radiation, and that alpha radiation ionizes the atoms in the air in a gap in a circuit. Okay, so let's draw a little diagram to help us really understand that. So what it is there's a gap in a circuit, and there's lots of little atoms in here, in our gap. Then alpha comes along from our source, so alpha comes along and it hits these atoms. So alpha from our source comes along and it hits these atoms. Now remember, alpha hitting an atom makes it ionized and creates charged particles. So our atoms now turn into ions. Now, because ions are charged, we have a charge flow, which is a current. So by alpha ionizing the atoms in the air, we can create ions. And because these ions are charged, we have a charge flow because this is a constant process. And if we have a charge flow, there is a current. So this ionization is what is creating the current in our circuit. But if there is a fire, the smoke from the fire absorbs these ions. It absorbs these ions from the gap and it takes them and the current drops. Okay, if those ions are being taken away, there's not as much charge flow anymore and our current is going to drop. And if our current drops, that signals the circuit to sound the alarm. Okay, so if our current drops, it sounds the alarm because the smoke has absorbed the ions, and the smoke alarm can therefore detect that there must be some source of smoke because it's losing all this ions, it's losing all this charge, it's dropping current, and that's how it detects smoke, which I think is a pretty cool application of alpha radiation. Okay, so the second application of radiation that you need to know is the application of beta. So actually, beta is used in metal foil production. So we have a radioactive source which sends out beta particles. The amount of beta that gets through the foil depends on the thickness of the foil. So let's say we have a beta source. So this is our beta source here. So that is giving out lots of lovely beta. Now that beta is being shot at some amount of grey foil, of metal aluminium foil. So this is our foil here. So our beta is being shot at the foil, and there's a detector on the other side. So this is our detector. Now, if a lot of particles get through, we say that the foil must be thin. If not a lot of particles get through, the foil must be thicker because it's absorbing more beta particles. So you can see that the amount of beta that gets through the foil depends on the thickness. The detector measures the amount that gets through, and if it's too thick, so there's a certain amount of beta particles that it picks up, and if it's too thick, if it doesn't pick up enough beta particles, the detector sends a signal for it to be re-rolled, for it to be re-thinned out. Okay, so if it's getting too little beta particles, if not enough beta particles are getting through the foil, it thinks, okay, the foil must be too thick. I'm not getting enough beta particles through. And so it sends a signal for it to be re-rolled. Now, the reason that gamma is not used is because it would pass through the foil unaffected. And it would not tell us any information about the thickness of the foil. It would just pass straight through because that's what gamma does. Gamma can only be stopped by lead or concrete. So gamma would not be appropriate. Alpha would also not be appropriate because it gets blocked by even paper or skin. So alpha is not going to make it through the foil. So alpha would be stopped here. Gamma would just go all the way through. So beta is the perfect radiation for this application. Just a note here with the smoke alarm, alpha is used because beta and gamma are not ionizing enough. They don't have enough ionizing power and they can't create the amount of ions that are needed for a current to flow. So as well as knowing which radiation is appropriate, we also need to know which radiations are inappropriate and why. That's very important. Okay, so let's move on to the second part of the content now, which is the activity of a source. So the activity of a source is the number of unstable atoms which decay per second. So how many atoms are we getting released per second? Now the unit of activity is called the becquerel, and it can be denoted by BQ. 1 becquerel is 1 decay per second. And as the nucleus decays, the activity drops. So as the nucleus decays more and more, the activity drops. We get less decays per second than we did at the beginning of the decay of the nucleus. But one thing that is really important with activity is that it's not possible to say when it will decay. We cannot tell, it's a completely random process, when our source will decay. But what we can say is that a certain number will decay in a certain time. So we can't say when, but we can say that we think that a certain number will probably decay in this amount of time because there are so many. So another way of expressing activity is count rate. So count rate is the number of decays recorded each second by a detector, such as the Geiger-Müller tube. And in this graph, we can see a graph of count rate against time. So how many decays per second? And in this case, they've actually done it in minutes. So you can see that the count rate between here and here halves. Goes from 600 to 300 to 150 to 75. But what you can see is that it goes from 600 to 300 in 45 minutes. This is going to be really important in a second. So we introduce this thing called half-life. Now, half-life is a way of scientists knowing how long it's going to take for that source to decay. But not just any time. It's the time that it takes for half of the nuclei to decay. Okay, so half-life is the time taken for half of the unstable nuclei to decay, or for the activity to half. It's the same thing. Or for the count rate to half. Again, same thing. So let's have a look at our graph here. We want to know how much time it takes for the count rate or the activity to half. So could you please put your answers in the chat? Have a think about what would happen between 600 and 300. What is the half-life of this substance? How can we tell the half-life from this graph? How do we work out? How do we work out the half-life from this graph? So remember, the half-life is the time that it takes for the count rate to half. Okay, so for the half-life of this specific substance that this graph has been created from, we want to take a certain count rate and half it. So let's start with 600 and go to what is half of it, 300. And what we want to know is how long it takes for the for the count rate to split in half. So from 600 to 300. So we mark this on our diagram. And we see that it takes 45 minutes for our count rate to half. So for it to go from 600 to 300, we see that it's 45 minutes. Okay, so just under our 50 minutes. And you didn't have to do it for 600 and 300. You could have done it for 300 and 150. And you can see that again, it's 45 minutes. Or you could have even done it for 150 and 75. And again, you see that it's 45 minutes. So you want to draw a line from the first count rate and draw a line from the second count rate and then join them up with a vertical line down to our x-axis. When it hits the x-axis, that's the time that it takes for the count rate to half, or the half-life. Okay, so that's how we work out a half-life from a graph. Now this is where it gets a little bit tricky. this is for if you're doing higher tier physics. So the count rate after n amount of half-lives, where n is just the number of half-lives, is equal to the initial count rate, the initial number of unstable nuclei, divided by 2 to the power of the number of half-lives. So let's go through a worked example to really understand what this talks about and what this equation means. A particular radioactive isotope has a half-life of 6 hours. So how we can write this down is T half, this means half-life, is 6 hours. We're going to write that down as our first bit of information that we've gained from the question. Half-life is 6 hours. A sample of this isotope contains 60,000 nuclei. So our initial count rate, or our initial number of nuclei, you can do it with either. Okay, count rate can be switched out for nuclei. You can have count rate or nuclei, they're interchangeable. So our initial number of nuclei is 60,000. Now we need to calculate the number of nuclei of this isotope remaining after 24 hours. So this is the final number of nuclei here. This is the final number of nuclei. And this is the initial number of nuclei. And they are related by this factor 2 to the power of the number of half-lives which have passed. So we want to know how many half-lives have passed. And because we've been given a time of 24 hours, we can see that that is equal to 4 half-lives. If one half-life is 6 hours, then 4 half-lives is 24 hours. So we know that 4 half-lives must have passed in 24 hours. It halves after 4 hours, it halves again after 8 hours, halves again after 16 hours, and finally halves again after 24 hours. So it's been through 4 half-lives in 24 hours. It splits the number of nuclei in 2 every 4 hours. So we know that n, the number of half-lives, is 4. So n is the number of half-lives which have passed, which is 4. N equals 4 because 24 hours equals 4 half-lives for this specific substance. Now we need to put n into our equation. So our equation is the final number of nuclei equals the initial number of nuclei divided by 2 to the power of n. Okay, so it's a nice way of representing the relationship between the final number of nuclei and the initial number of nuclei after a certain number of half-lives have passed. Now we know that n is 4 because it's the number of half-lives which have passed. So we can replace n with 4. So now we have 2 to the power of 4. And we know that 2 to the power of 4 is 16. And you can do this on your calculator. So we can replace 2 to the power of 4 with 16. And we don't have this ugly 2 to the n anymore. Now we also know that the initial number of nuclei, is 60,000 before any decays, before any half-lives, is 60,000. So we can replace initial number of nuclei with 60,000. so that we have an equation, final number of nuclei equals 60,000 divided by 60. So our final number of nuclei after 4 half-lives is 3,750. Now, I wouldn't worry too much about this equation. I've seen it come up never in any of the past paper questions that I've been looking through. So it is very rarely tested, but it is a technique that we need to know, and it is an equation that we need to know how to apply. Okay, so let's have a look at this question. What is the half-life of a sample where the activity drops from 1,200 to 300 in 10 days? What is the half-life, do we think? Well, the half-life of 1,200 is 600, and half of 600 is 300. So in this time, in 10 days, we have 2 half-lives. We have it halving once to 600 and halving again to 300. So it's halved its activity twice. It's gone from 1,200 to 600 and 600 to 300 in 10 days. So if 10 days is 2 half-lives, then 1 half-life must be 5 days. So 1 t-half, 1 half-life is 5 days, because in that 10 days, it halves twice. Okay, so let's have a go at some more example questions. But before we do that, I'm just going to answer a few quick misconceptions. Why does it only emit a helium nucleus instead of an entire helium atom? That's just the nature of alpha. Alpha doesn't have any electrons. It's just emitting the nucleus. It just deals with protons and neutrons. Beta is dealing with the electrons. It's just the nucleus. Where do alpha particles come from? Okay, so alpha particles come from inside the radioactive substance. So we don't know kind of really why it happens, but it releases these helium particles, these alpha nuclei, randomly, sporadically. But they come from inside the source. Can you see alpha and beta particles? No, but you can trace them with very kind of advanced software in labs. How do you determine the type of radiation that an atom will emit? Okay, this is a very advanced technique which scientists have done over years and years, and the way that you determine it is just experimentally. So there's no way of kind of telling, you just have to experiment with it and find out which one it emits. Okay. Emit just means to kind of give out. So let's match these up. Which one describes alpha? Which box on the right describes alpha? Well, alpha we know is 2 protons and 2 neutrons, otherwise known as a helium nucleus. So 2 protons, because 2 is our atomic number, and 4 protons and neutrons. Beta is an electron from the nucleus, and gamma is electromagnetic radiation. Okay, so we've been given a diagram here, and we've been asked to fill in the gaps. So, which one passes through all three materials and only gets stopped by lead? Which one passes through the paper but gets stopped by aluminium? And which one gets blocked by paper? Hopefully we know that gamma passes through all of them and only gets stopped by lead. Beta passes through the paper but gets stopped by the aluminium. And alpha gets stopped by the paper. So this is all to do with the penetration of the radiations. Gamma penetrates the most. Okay, so here in this question, you've been given a statement. The following statement about alpha particles was written by a student, but the statement is not correct. The student says that alpha particles can pass through a very thin sheet of lead. We need to change one word in the statement to make it correct. So which one word would you choose to change to make this statement correct? And what would you change it to? Alpha particles can pass through a very thin sheet of lead. Okay, so there's two different answers that you could have here. You could either change the can to can't, so alpha particles can't pass through, or you could have said that alpha particles can pass through a very thin sheet of paper, not lead. So you could have changed the can or you could have changed the lead. Either would have been acceptable. Okay, so we're going to stop there for today. And next week, we're going to be moving on to applications of, actually, we still have 15 minutes. Let's do some more past paper questions. So here we've been given a graph of how the count rate from a sample of uranium-238 changes with time. Now, one thing I'm just going to show you about this is that uranium-238 means that it's uranium-238, like this. So all that means is that the mass number is 238. So here we have a graph of how the count rate changes with time. Now the graph can be used to find the half-life of uranium-238. They've told you that the half-life is 4,500 million years, where the x-axis is measured in millions of years. Where would you draw the line to show that this is true? What line would you draw on the graph? Or what lines would you draw on the graph to show that the half-life is 4,500, given that the initial count rate is 1,000? Where would you draw your lines? Remember that half-life is where the count rate halves. So if it starts at 1,000, we want to find the time at which it gets to half of that. And half of 1,000 is 500. So we've taken our initial count rate and we've halved it. Half of 1,000 is 500. And at 500, we draw a line to the curve. Then from the curve, we draw another line down to the x-axis. And we can see that it hits the x-axis at 4,500 millions of years. So we've proved that the half-life is 4,500 years, because that is the point at which it hits the x-axis. So again, we've taken the initial count rate and we've halved it. The time at which it is completely halved is the half-life. Now, you could do this with other points on the graph. So for example, you could have taken 800 and seen at what time we hit 800. And you could have taken the time at which 800 is halved, so 400. And that would have been the same amount of time. So it's really up to you where you take the half-life, but what I would say is probably easiest is to take it from 1000. I would say it's probably easiest to take it from 1000 because then you don't need to do 2 readings off the graph, you only need to do 1. Could do it from 800 to 400, 700 to 350, anywhere where there's an initial reading and it's halved at some point later on. So you can see that if you started with 1000 and went to 500, you got 4500. If you started with 800 and went to 400, you still have a 4500 difference. Okay, so this graph shows how the count rate from a source of alpha radiation changes with time. At time 0, it has a count rate of 100. What is the count rate after 4 hours? Put your answers in chat. What do you think the count rate is after 4 hours? Okay, so the count rate after 4 hours is, and we're going to draw a line up from our x-axis at 4 hours, and we're going to draw a line across from the point on the graph to the y-axis. And we find that at 4 hours, the count rate is 40. So if you said 40 counts per second, then that would be correct. Okay, so again, we have a kind of matching activity. And on the left, you have the type of nuclear radiation, alpha, beta, or gamma. And on the right, you have a property of that radiation. Draw 3 lines to match up those in list A with something in list B. And if you don't want to type in the entire thing, then you can just do 1, 2, 3, 4, and tell me which A, B, or C matches with which number. Okay, so for this, alpha is very strongly ionizing. Alpha has the highest ionizing power. It is able to knock electrons out of atoms and make them charged. Beta has the same mass as an electron. So beta is an electron or a beam of electrons. And gamma passes through 10 centimeters of aluminium, because gamma can pass through any amount of aluminium, but it will be stopped by lead or concrete. Okay, a radioactive source emits alpha particles. What might this source be used for? Could it be used to monitor the thickness of aluminium foil? Could it be used to make a smoke detector work? Or should it be used to inject into a person as a medical tracer? Which one do you think would be the most appropriate source for alpha? Okay, so the most appropriate source for alpha would be to make the smoke detector work. As we saw earlier on, alpha is the most appropriate radiation to make the smoke detector work, because alpha is the most ionizing. It's able to knock those electrons out and charge those atoms up. And as we know, when we have a flow of charged particles, we create a current. And so a current is needed to make the smoke detector work. Gamma and beta would not be appropriate for a smoke detector because they simply aren't ionizing enough. Okay, so this exercise, this past paper question, talks about the application of beta, which we looked at earlier, which is how can we test whether the thickness of the foil, or indeed it could be any other material such as cardboard, is the correct thickness. So how do we control the thickness of our material? Well, we said that we shine or kind of pass a beta source through. We pass these beta particles through our material, and the detector picks up a certain amount of particles. If it gets the correct amount, we know that the thickness is good and the cardboard can be passed through. However, if we are not getting enough particles through, we know that the thickness must be too high. So this cardboard passes through this gap and the beta source is passed through it. The table gives the detector readings over 1 hour. Between 8 and 8:30, the cardboard is produced at the usual correct thickness. So this is correct, correct, correct. However, it suddenly drops from an average of 150 to 101. So the reading 101 is not good. It's way too low than it should be. So explain how you can tell from the detector that the cardboard is thicker than usual. Well, we can tell that the cardboard is thicker than usual because less beta particles are able to get through the cardboard. And therefore, the cardboard must be absorbing the particles. Okay, so we know that the reading suddenly drops, and because we aren't getting enough beta particles through, those beta particles must be absorbed by the cardboard. So we know that the cardboard is too thick and it needs to be re-rolled. Now this control system would not work if the beta was replaced by an alpha source. So why would the control system not work if we started using alpha? Well, alpha is blocked by skin or paper. It would not be able to get through cardboard. Okay, it can get through air, but it would be blocked by paper or cardboard or any such material. Skin, paper, cardboard, it would simply be blocked and it would not pass through the detector. The detector would not be able to make any readings and it would just be completely inappropriate to use alpha. So we have an alpha source here and it would just simply get stopped at the cardboard. It wouldn't be able to go through the cardboard and no readings would be able to be taken. So the only radiation that we can use here is that beta is beta. Okay, let's go through this question. So what name is given to the center of an atom? So if we remember, our final model of the atom is this central something and electrons orbiting around it. So what is the name given to the center of the atom? What is the name given to that dot in the middle where most of the mass is stored? Put your answers in the chat. What do you think the name of the center of the atom is called? Okay, those of you getting the correct answer. The name given to the center of the atom is the nucleus. And before using a radiation source, a teacher asked her class whether there was any way that she could reduce the amount of radiation that the source emitted. And 3 students gave their answer. Keep the source in the freezer, put it in acid, or you can't do anything to change the amount. Well, clearly student C was correct. Putting a source in a freezer or putting it in acid will not destroy the radiation. The source will give out radiation no matter what you do to it. It's random and we can't predict it. So that marks the end of today's webinar. Hopefully you learned lots today. And as always, this session is recorded and will be uploaded onto YouTube as soon as possible. Next week, we're going to be moving on to looking at nuclear radiation in medicine and its applications in medicine. And if you guys do want any kind of one-to-one, more personalized tutoring with a tutor like myself, then that's something that MyTutor offer and you are able to sign up for that. So do keep that in mind. Thank you all for attending today's webinar and I'll see you next week. Bye.